This problem is a momentum balance problem. There's a rocket motor with a combustion chamber and a nozzle. At point 1, the area, velocity, and pressure are given. That is at the joint between the combustion chamber and the nozzle. At point 2, the pressure is lower, but the velocity is higher and the area is lower. In both cases, the mass flow rate is 300 pounds mass per second. So this is clearly a compressible flow situation since the area times the velocity is not the same. But the mass flow rate is the same in both cases. That's why the nozzle is converging and diverging. In this problem, we are asked for the thrust and also the force at the joint and whether that is compressive or tensile. To get the thrust, we need to look at the pressure forces and the convective forces, and we will take the whole motor as our system. Though the area at point 1 is meant to be at this connection between the combustion chamber and the nozzle, we will take that to be the same as the area on the top at A1. So in this case, we have ambient pressure acting in this direction on an area of A1, and at the bottom we have P2 acting on A2, and we also have P ambient acting on A1 minus A2. Pressure always acts on the system, so the thrust will be given by the difference between those two pressures. I will define up as positive, so P2 A2 plus P ambient times A1 minus A2 is acting in the upward direction, and then minus P ambient times A1 is acting in the downward direction. There is one convective out term, so that is minus the mass flow rate times the velocity at V2, and that is in the negative direction, so times negative V2. Those three pieces together make up the thrust of the rocket motor. The force at the joint requires a different system boundary, so for that we'll draw a system boundary that goes through the area at A1. Okay, so to get the force at the joint, which we will assume the forces are tending to tear the nozzle and the combustion chamber apart, so the force will have to act in this direction to hold the nozzle onto the chamber. A momentum balance in this case says that 0 is equal to the rate of change of momentum with respect to time of our system, and that is equal to, again we have P2A2 plus P ambient times A1 minus A2 acting in the upward direction, and then at point 1 we have P1 A1 acting downward. Those are the pressure forces. We also have plus the force of the joint acting to hold it together, and then we have two convective terms. At point 1 the mass flow is coming in, so plus m, and that's coming in at a velocity of negative v1, and then at point 2 we have minus m, leaving at a velocity of negative v2. Putting all of this together, we can solve for the force at the joint, and that is equal to m times v1 minus v2 plus p1a1 minus p2a2 minus p ambient times a1 minus a2. You'll see the terms that make up the thrust are part of this, but then there are other terms in addition to the thrust that are affecting the force at the joint. Notice that V1 is less than V2, so the convective terms would actually decrease this force at the joint, but the pressure terms act in the opposite direction, net, and are significantly greater. Therefore, the force at the joint ends up being positive.